Hello, hello everyone, welcome back to the channel. So today we are going to take a look at this cool question called Cool Graph from the recent refact.ai Codeforces round. So the question says that you are given an undirected graph with n vertices and m edges. So you can perform the following operation at most two times max of n comma m times. So what the operation states is that we can choose the three distinct vertices a comma b comma c, and then for each of the edges a comma b, b comma c and c comma a, do the following. If edge does not exist, add it, and on the contrary, if it exists, remove it. So the operation is basically that. So see here. So if this is vertex a, this is vertex b, and this is vertex c, suppose how many states are possible. Suppose this thing a b c, a b c. Okay, without loss of generality, we can swap these vertices. So like we can do this. So if you try to argue that this case is different than this case, then it is not correct, because I can always swap this b and a to get the same structure. So yes, um, basically these are the three basic cases. So if I try to perform operation on this set, it will become like this, right? Because there was an edge in a and b, we removed it and added these two edges. Here it will be like there won't be any edge remaining, and here it will be like this. So a b c, a b c. So this is basically what the operation states. And why I am drawing these all the three cases explicitly, you'll see. So yeah, uh, so let us read a question further. So graph is called a cool graph if and only if one of the following holds. So if the graph has no edges or the graph is a tree, so you have to make the graph cool by performing the above operations. Note that you can use at most two times max of n comma m operations, and it can be shown that there always exists at least one solution. So okay, so here what we will try to do is that, suppose I don't know if when the graph is cool, when I will make that graph cool by performing some operations, will it be a disconnected graph? Will it be a disconnected graph? Disconnected graph in the sense there will only be the vertices and no edge, or it will be a tree. I don't know that, right? So uh, one way to know is that, suppose uh, so sorry for the disturbance. And where were we? So we don't know that will it be a disconnected graph or a disconnected graph having no edge, or it will be a tree, right? So what we can do for that is that, suppose, see here, in these three cases, when you try to apply operation on this graph, okay, so when you try to apply operation on these three vertices, number of edges increase by 1. Okay, it goes up by 1. If you apply operation here, number of edges goes down by 3. Okay, and if you apply operation here, the number of edges go down by 1. Okay, so If you want to make it disconnected, then you don't want to perform this type of operation, right? You don't want to do that, because ultimately you are ending up with one extra edge, so you don't want to do that. So we will not do that. If we want to know that is it possible to make the graph disconnected with having no edge. So what I can notice is that I will only select the three vertices, one of which or three of which has the degree 2, right? So degree 2, and three of, or you can say two of which, basically in the triplet, one vertex should be such that its degree is 2, right? So I will try to perform those operations. So what will I end up with? So let's see. So when I apply operation on the nodes which has degree greater than or equal to 2, so basically you can get some vertices which are not connected. So suppose some vertices which are not connected at all, or some vertices like they will have degree greater than or okay, sorry, degree less than or equal to 1, right? So because we removed vertices uh, all the vertices, or you can say all the edges from a particular vertex if its degree was 2, right? So we won't have this type of nodes after performing those operations till there is no node left with degree greater than or equal to 2. So this is only the case. So suppose I'm left with this kind of structure. Suppose some free nodes, right? This is one general case. You can take whatever you want, but these are some pairs which exist, and these are some nodes which have degree 1 that exist. So suppose our graph converts like this. So can I make it that this graph disconnected completely? Can I make this graph disconnected completely? Yes, if any pair is not there. Okay, so if at least one pair is there, answer will be no, right? No if pair is there, connected pair of vertices you can say, and yes if no pair, right? And what if pair is there? Can we convert it into a tree? So let us see. So we will uh, consider this thing. We will consider this thing and make it the base of our graph. So what I am meaning by the base here is that, so I will let us name this as x, this as y. So this as y, and when I select these vertices which are having degree 1, uh, suppose first I'll take this vertex, then take this vertex. With these two vertices I'll make a pair of them, so I will make operation on them. So what will happen if I select this? So something like this, right? Okay, so something like this will happen. And okay, now my this edge which was there, uh, this edge, okay, where is it? This edge, this has vanished, right? So to x and y to happen to be the base of my graph, y should be here, right? So y should be here. Okay, so I'll swap y with this and then select this vertex. Then what will happen? This edge will be gone, and these edges will be formed, right? And then I'll swap this y with this vertex, right? Makes sense? Okay, so let me redraw this. Redraw this. So it will be something like this is x, this is y, and there are two nodes hanging from the y. Okay, so this is the base. Now we will select okay, now we will select only y and these two vertices. Okay, I'll make operation on this thing, this and this. So what will happen then? The thing which will happen is that this edge will be gone and these edges will be formed, right? So this time there is no need to swap the y, right? Because x and y still have the edge, and it's the base of the graph. And now I will perform the same operation with these three nodes, this thing, this thing and this thing. So finally my graph will be like this edge will be gone and these two edges will be drawn. So finally what will it look like? It will be x, this will be your y, two nodes hanging from the y, and and this node is y, and this thing. Is this a tree? Yes, it is a tree. So this is basically the procedure that we will follow, and what will be the number of operations that we will make. So to perform step 1, which is remove all the vertices with degree greater than or equal to 2, I can notice that I am always decreasing number of edges by at least 1, right? So here down by 3, here down by 1. So to complete the first step, the number of operations I will make is less than or equal to m, right? Okay, so what about the second step to make it as a tree? So in one operation, at least I am able to get one vertex in my tree, right? One vertex included in my tree in one operation, at least. Okay, at least one vertex included in the tree. Okay, so when I select the degree vertex with degree 1, this will be the case, and if I select the pair, then two vertices will be included in my tree. So I can argue that it will be less than or equal to n, right? So my total number of operations will be n plus m, less than or equal to n plus m. Can I argue this? Yes. So this is basically less than or equal to 2 times max of n comma n, right? So this is basic mathematics, or you can prove this by without loss of generality, taking n as greater than n. So this is the thing that we have to do. So this is the bigger picture of what we will do. Okay, bigger and okay. So first we will try to make, this is step 1 and this is step 2. In step 1 we will make degree of every vertex less than or equal to 1, and in step 2 we will create base as this x and y, which will always remain connected to each other, and we will try to merge remaining vertices, which will have degree is equal to 0 or degree is equal to 1, right? So degree is equal to 1 means it will be a pair, and if degree is equal to 0 means uh, it is just one hanging vertex in the air, so it doesn't has any edge. So let us head towards the implementation is quite easy, you can say. So basically reading the input. And if m is 0, so basically there are no edges, then graph is already cool, so outputting 0 and continuing for, or proceeding further to the further test case. So this is again taking the input, and I am modeling input of graph as this adjacency list. Okay, so storing the steps in this answer vector, and this is step 1. Okay, this for loop is step 1. So let us see what is it doing. So while g of I dot size is greater than or equal to 2, so what it suggests is that degree of that vertex is greater than or equal to 2. So I will pick the vertex, pick the first vertex and then erase it, then pick the second vertex, which will be the which will be connected to the p. So not p, or basically it will be connected to I, and I will erase q from I will erase I from p. So basically what we are doing here is that, so basically this is vertex I, this is vertex p, and this is vertex q. Okay, so in the adjacency list of I there are two vertices p and q. So basically when I'm calling this star g of I dot begin, it is returning me p, and then I'm erasing the first vertex, so it will erase p, and then when again I'll call g star of g of I dot begin, it will give me q. Okay, and then I'll apply operation I comma p comma q. Okay, and when I'm applying operation I comma p comma q, I have to erase I from p from I, q from I, and I from q. And one more step, if there happens to exist an edge from p to q, we have to remove it. And if there is no edge, then we have to insert that edge. Okay, so basically this is doing that thing. So till here we are erasing p from I from p, q from I, and I from q. And here I am inserting edge if it was not there, and deleting it if it was there. So this part, so step 1 is completed. Okay, so my graph will look like somewhat like this. So some disjoint components with each vertex having degree less than or equal to 1. And yes, I'm checking if there are any pairs or not. If there are no pairs, then I'm good to go, because graph is disconnected with having no edge. And if g of I dot size is equal to 0, so degree 1 dot pushback I. And uh, if g of I dot size is not 0, means there exists a pair. So what this condition is doing is that it is preventing the duplicate pairs to get pushed back to the pairs vector. So what is it doing is that, so look here. So suppose my 2 comma 3 is the pair, right? So when I'm iterating from I is equal to 1 to, let's suppose, n, so when I'm at 2, I will because g of 2 dot size is not 0 because it has an edge, so I will push 2 comma 3. And when I'm at 3, then again I'll push 3 comma 2, right? So I don't want to do that, so that's why that check is necessary. So preventing the preventing the duplicate values, it is doing that. And if pairs dot size is greater than 0, so basically I'm selecting any element pairs dot back. Okay, so simply one element, you can say one element from the pairs x and y, making them as a base, then popping them, so we don't have to merge them into them, right? So it is a base. So for every vertex which is having degree 1, we will push back x comma y comma entry, and we will swap y with that entry, right? So and then finally uh, pushing the pairs, pushing the remaining pairs and the y itself. So that is basically the thing, and finally outputting the answer dot size. And this is basically the syntax to get the arguments of the tuple, means the first element, second element and the third element, and finally outputting them. So yes, so this was very good question, I would say. uh, hope I hope that you enjoyed solving this question and listening to the solution as well. Thanks for watching the video, and this was really a good question, I know. Consider liking the video and staying subscribed to the channel. See you again.